In this video, we're continuing section 3.1 on the definition of a function. And in this video, we'll discuss how we can find the range of a function. So in general, finding the range of a function is a hard problem, but there are two special situations where we can solve for it quickly. The first situation, method one, I'm going to call, is if we know the graph. If we know the graph, or we can determine it, then graph it, and then use the graph to find the range. And the second method says that, if we don't know the graph of a function, so if we don't know the graph, then we're going to try isolating for the x. So it turns out that that only works for certain special functions, and it requires the function has an inverse, which is something we'll talk more about in section 3.5. But for our purposes right now, if we encounter something like this where the graph is unknown, then to find the inverse, we're going to try isolating the x. And we'll see how that works with an example. Okay, so let's take a look at example 4 here, which says find the domain in the range of this function. So finding the domain in the range of this function. Well, so this is a quadratic. It's a quadratic, and I see the leading coefficient is positive, so we know it's some upward-facing parabola. So to find the range of this, we would need to find the vertex of the parabola. Okay, and we can do that by completing the square. Okay, so we're going to complete the square here to get the range. Alrighty, it turns out if we do complete the square, I'm actually going to skip those steps. We reviewed that in chapter 2, but we'll end up getting this. After we complete the square, we'll get this. So now, looking at that form, let's say what the vertex is. So the x-coordinate is -8, right? Because that's what I plug in for the x to make this part be 0. And if I do plug in -8, the y value ends up equaling, well, we get 0 and then -6, which is -6. So my vertex is at -8, -6. So that is somewhere here in quadrant 3, -8, -6. And we already said it was an upward-facing parabola. Okay, so something like this perhaps. All right, so now we can say what the range is. The range, so the possible y values, the smallest possible y value happens to be at the vertex, and it's -6. We do achieve that y value, so it's closed. And then the y values get bigger and bigger and bigger forever, so they go onwards to infinity. And that's my range. This question also said find the domain. So let's write what the domain is. In fact, I had a section already here designated for the range. So let me move my answer. Whoops. Let me move my answer to that designated range section. So range, I can write here next to range. And now let's do domain. Well, domain is easier. Looking at this function, there are no restrictions on what x can be. There's no restriction on the types of numbers I'm allowed to plug in. So my domain is just going to be -infinity to +infinity. So this is my range. This is my domain. And I can also see that that's the domain from the graph. From the graph, there's clearly no x value that gets skipped along the way. So the domain is everything. Okay, so this is a situation where we use method 1. We could graph this function because it's quadratic, so we use that graph, and in particular the vertex, to get our range. All right, let's try another example. Find the domain in the range of this fractional function. So this is something called a rational function. A rational function is when you have a polynomial divided by another polynomial. Okay, so in our class, we haven't talked about what the graphs of functions like this look like, although they are things that we could ultimately do. So for our purposes right now, let's say we don't know how to graph this perhaps. And if that's the case, let's try method 2 here. Let's try isolating the x to find the range. But let's get the domain first perhaps. So for the domain, let's think about the restrictions. So, well, I see one possible restriction right here, which is a denominator cannot be 0. So because the denominator can't be 0, that means x cannot be equal to -5/2. Because that's what I would plug in for the x to make the denominator be 0. Okay, so that's the only x value not in the domain. So my domain is negative infinity to negative 5 halves, parentheses, union, parentheses, negative 5 halves to positive infinity. Essentially, the domain is everything except negative 5 halves. Okay, now let's tackle the range. So we said, the graph here is not something that we know as easily. So let's try our other method. Let's try isolating the x. So how does that work? So I'm going to rewrite f of x as y. So we got y equals 4x minus 15 over 2x plus 5. And I'm going to try to isolate the x. So maybe to get rid of the fraction, I'll multiply both sides by the denominator, 2x plus 5. So let's multiply both sides by the denominator. And now on the left side, I can distribute y to each of these terms. So that gives me 2xy plus 5y. On the right, my 2x plus 5 cancels out on the top and on the bottom. So 4x minus 15 there. And to isolate x, let's get all of the x terms perhaps on one side of the equation, and then all of the terms that don't have an x on the other side. All right, so let's see, how do I want to do this? So maybe I will bring the 4x, in fact, maybe I'll bring the 4x over to this side. All right, so I'll get 2xy minus 4x, and I'll move 5y over to the right by subtracting it. So that'll give me negative 5y minus 15. And now that I have all the x terms on the left, let's factor out that x that's common. That'll leave me with 2y minus 4 equals that negative 5y minus 15. Now I divide and I get x equals negative 5y minus 15 all over 2y minus 4. So at this point we have x isolated. X is by itself, and there are no x's on the other side of the equation. That's really important when we isolate that variable. We don't want any x's lingering on the other side, because then we haven't really isolated it. Okay, so now what I'm going to do, that I have x isolated, is think about the fact that, well, when I find the range, I want to know what y can be. But because x is isolated, and I only have y's on the other side, I can kind of flip it in terms of how I normally think about domains. I'm going to think about restrictions now, but on y. Restrictions on y, because the range has to do with what y can be. So now when I look at this fractional thing, well, there's one possible problem, which is what if that denominator equals 0? So there's one restriction. What would make that happen? Well, it's if y equaled 2. So y better not equal 2, because that would make this fraction undefined. I would be dividing by 0. Okay, so that's the one restriction on y. So I'm ready to just take that and write my interval notation now. It's everything except 2, so that's negative infinity to 2 parentheses, union 2 onwards to infinity. Everything except 2, and that is my range. All right, so to recap, when we're trying to find the range but the graph is unknown to us, try isolating for the x. Because if we can get it isolated, well, we'll have only y's on the other side, and then we can think about what the restrictions there are on y, and that can lead us to the range.